Remember that, guys, we split the network into two parts. One of them was network edge, and the other part was network core. So far, the network edge consists of two layers, which are application layer and the transport layer. So we completed these two layers. Now we are going to move to the core network, starting with the network layer. So the first things that we need to study is to understand the main principles behind the network layer services. What are the main function of this layer? More specifically, what are the service that is provided and what are the service models for this case? And there are two important functions in this layer. The first one is the forwarding and the other one is routing. So the question is, what is the difference between forwarding and routing? They seems to, pretty much looks like each other, but there are some differences that we're gonna see. And the next important topics is, in terms of device, we use a router. So router is a network layer kind of device. So the question is how a router works. What are the main architecture of this router? We are going to learn a main block of a router. Then we will talk about the core part of these layers, which is the routing algorithms. We transmit the messages in terms of packets from source to destination. But the question is, there are many different paths that we can transmit this packet from source to destination. How do we select the path to deliver this packet to the destination, which is conducted by routing algorithms? And then we have different kind of transmission types. The first one is the broadcast, multicast, unicast, and we're going to look at specifically how the broadcast and the multicast algorithms work in this layer. So let's look at the outline. First, we will start with introduction, some background information about this network layer. Then we have two architectures that we need to study in terms of network type. The first one is virtual circuit networks. The other one is the datagram networks. So we're going to compare both, what are the pros and cons of each of these architectures. And then, as I mentioned, we're going to move to the next topic, which is architecture of a router, how a router works, what are the main blocks of a router. And the last topic for today is going to be IP protocol, which stands for Internet Protocol. So we use a lot this term, this protocol, and we need to study the details of this protocol, including the format of this protocol and different version of that, including the IP version 4 and the IP version 6. And how do we handle the address issue in this case? And then some protocol related to the IP, which is the ICMP. And the last topic is going to be IP version 6. So what are the main features of the IP version 6? Why we are moving from IP version 4 to IP version 6? We are going to answer all these questions. And then we are done for today. Okay, so let's start with the introduction. As you remember, at the application layer, we generate the messages and we split these messages into the segment at the transport layer. Now, the main function of the network layer is transport segments from sending to receiving host at this layer. So in this case, on the sending side, we encapsulate the segments into datagrams. We call it datagrams. And we pack these segments into datagrams at network layer. And then we transmit, send to the receiving host. On the receiving side, we deliver these segments to the transport layer by removing the, the header of the network layer. So network layer protocols is in every host and router. So that means the network layer needs to be included in every end system, as well as the router, which is part of network core. And the router, when it receives datagrams, it first of all examines the header fields in all IP datagrams, and then according to the header information, it forwards to the appropriate output. Let's look at the animation together, how a segment is transmitted from sending side to a receiving side. So as I mentioned, network layer is everywhere, including the end system as well as the router, which is part of a core network. Okay, here we go. We have datagrams that pass through all these routers, and it delivers to the receiving host, and then hand over to the application layer. So there are two important network layer functions. The first one is forwarding. The second one is the routing. So what is a forwarding? In forwarding, we move the packets from router's input to appropriate router output based on the header information. So you can think like forwarding is an function that happens within a router. On the other hand, routing, it determines the route taken by the packets from source to destination. So it is responsible for selecting a path from source to the destination and then deliver this packet to the destination host. If you want to make an analogy between routing and forwarding, routing is remember in one of the previous lecture, we give an example of travel trip, let's say from Istanbul to Ankara. So routing in this case is process of planning trip from source to destination. In our example, in travel example, you organize, you plan your trip from your home at Istanbul to Ankara office, for instance. So you plan the complete process of from your home at Istanbul to your office at Ankara. On the other hand, forwarding is just a process of getting through single interchange. Forwarding, because in this travel, you need to either take a taxi cab from your home to the airport, and then from airport you take the airplane to the Ankara airport, right? And then from Ankara airport to the office, you take maybe shuttle or taxi or your rental car. So in this case, forwarding is just one of these process. For instance, like going from your home to the Istanbul airport. So this is the forwarding, is process of getting through a single interchange in this end-to-end trip. Let's look at more detail to see how the what is the routing and the forwarding. First of all, as I mentioned, so the routing algorithms we have in the router, and it determines end-to-end path through the networks. So it plans the whole path from source to destination. On the other hand, we have a forwarding table that is responsible for local forwarding at this router. For instance, as a router, you receive a packet, and as you see in the packet, we have a header, and in this header, we have some value, which is the IP address. So you look at this range. So based on this table, based on this table and the header information, you forward, you direct this packet to the appropriate output. If this is within like this range, then you direct this packet to the number 2 output. So this is called forwarding. But the routing is from source to destination. So we have a different type of structure. We are going to mention about that. So that's why some of them may require connection, the other may not require connection. So let's look at the connection setup perspective. So this is the third important function in some network architectures, such as ATM, frame relay, and X.25. So before the datagrams flow, before we start to exchange the datagrams, to end host and intervening routers, they establish some virtual connections. So in this connection, the routers get involved in this connection setup process. So let's compare the network versus the transport layer connection service. In the network layer, we connect, this connection is between two hosts. On the other hand, the connection between two processes is done in the transport layer. So at the transport layer, we have a logical communication between processes, whereas we have a logical logical communication between two hosts at the network layer. So let's look at now study the network service model. The question is, what service model for channel transporting datagrams from sender to receiver? So there are two types. The first one is for the individual datagrams, and the second one is for flow of datagrams. So some example services for individual single datagrams is guaranteed delivery and guaranteed delivery with less than 40 millisecond delay. So we have a restriction in terms of delivery as well as the delay. But when it comes to flow of datagrams, so in order datagram delivery, guaranteed minimum bandwidth to flow, and restriction on changes in inter-packet spacing. We have packets we transmit back to back, but sometimes the spacing between these two packets, consequent packets, may change. So therefore, we need to put some restriction on this inter-packet spacing parameter. Let's look at some network layer service models. And the first one is, of course, the internet. So it utilized the best effort service model. So, there's no guarantee. It tries its best to deliver your packets to the destination. Let's look at each of these parameters. The guaranteed in terms of bandwidth, no. So we cannot guarantee any kind of bandwidth for that specific packet, and we cannot provide any loss guarantee, and the order also is not guaranteed. So let's say my message consists of 6 packets or datagrams in this case, and I label each of them from 1 to 6, and I transmit packets to the destination. I send these packets to the destination, but because of each of packet can take different path, they may arrive at different times. So the first one, let's say number 5, packet number 5 arrive, then third, then second, then sixth. So it can be delivered out of order. And we should have a mechanism to put back this in order at the receiver side. So that's why in this internet, we cannot guarantee the delivery of in order packet. So timing also is not guaranteed. So it tries its best basically, because of each packet can take a different paths to reach to destination. Congestion feedback, no, we don't have any kind of this kind of feedback from receiver to the sender, but we can infer the congestion via packet loss or delay. And another technology is called ATM, which we utilize for mostly in financial banking transactions. So this has a 4 different service model like CBR, VBR, ABR, UBR. So variable bit rate, arbitrary bit rate, and so on. Let's just look at one of them. For instance, the CBR, it provides a constant rate in terms of bandwidth. It guarantees the loss, packet loss. It guarantees the order of the packets, and it guarantees timing. And there's no congestion because it's guaranteed service. And so, depending on the service model, ATM, 4 different service model. One of them is CBR. Let's look at another one like ABR. It provides a guaranteed minimum bandwidth, cannot guarantee the packet loss. It guarantees the in-order packet delivery, and it doesn't provide the timing. And congestion feedback is available in this case. Remember, they utilize some specific bits to tell the level of the congestion that happened at the network. Okay, so after this introduction, now we are ready to dive into the details of this network layer, starting with virtual circuit and datagram networks. So the first one is the connection and connectionless service. Datagram networks, first of all, it provides network layer connectionless service, and virtual circuit network provides connection service at network layer. So it's pretty similar to the TCP UDP connection oriented and connectionless transport layer services. Remember, at the transport layer, we have the TCP and UDP, and TCP was a connection oriented service and UDP was connectionless transport layer services. Similarly, we have a connectionless network layer service, which is datagram network, and we have a connection oriented service at network layer, which is the virtual circuit network. But of course, there are some differences in terms of some feature. First of all, the service is provided from host to host at the network layer. and there's no choice. Network provides one or the other. At the transport layer, you can easily switch from TCP UDP, but at the network layer, it's not easy because it's a part of infrastructure, so you cannot change it. So your network either select datagram network or the virtual circuit network. And when it comes to the implementation, the datagram network and the virtual circuit network are implemented at the network core compared to the TCP UDP, where they are implemented in network edge. Okay, so let's study the details of virtual circuit networks. So these actually, originally, it was developed for the telephone circuits that you had. I don't know if you guys remember at your home or office, this landline, you know, the wired telephone. So it's based on source to destination path, and it behaves like a telephone circuit. So the performance wise, yeah, it's similar. The network actions along source to destination path, and network action are taken along the source to destination path. So in this virtual circuit, because they're connection oriented networks, so we need to first set up a call and then, you know, exchange data, and then we need to close this connection for each call. And in this case, so it consists of three steps basically: call setup, data exchange, and then tear down for each call. And in this type of networks, each packet carries VC ID. So VC, virtual circuit identifier, is the ID number. Every router on source destination path maintains state for each passing connection. So we have a router throughout the path from source to destination, and each router, every router on this path, they need to keep the state for each passing connection that I'm going to show you. So, and because this is a connection oriented, so some of the link and router resources, such as bandwidth and buffers, sorry guys. Sorry guys. Can you see the screen?
Yes, we can.
Okay. So, because this is a connection-oriented setup, so some of the link and the router resources, such as bandwidth and buffers, may be allocated to that specific virtual circuit. So, because it needs to provide some guaranteed services, so that's why we allocated some dedicated resources to that specific virtual circuit. When it comes to the virtual circuit implementation, VC consists of three entities. The first one is path from source to destination. The second one is a VC numbers, and one number for each link along with the path that I'm going to show. It's similar to IP address like in datagrams network. And the third one is the entries in forwarding tables in routers along with the path. So packet belonging to the virtual circuit, they carries VC number. And the VC number can be changed on each link, of course. And this new VC number comes from forwarding table. Let's look at the VC forwarding table. As you see, we have a packet, packet from this source to this destination, and we have a specific path that is set up. So as you see, each link has a different VC number. This one has a 12, this one has a 22, and this link has a VC number of 32. And these are the interface number of router 1, 2, 3. So let's look at the forwarding table, how the forwarding table keeps track of these states. Let's say we have an incoming interface, which is 1, and the incoming VC number is 12, as you see. So you're going to forward this to the outgoing interface, which is 3, and the outgoing VC number is 22. So it keeps track of this VC as well as the interface number for incoming as well as the outgoing. Okay, let's look at how we set up the connection first, and then data exchange, and then tear down or closure of the VC circuit. So let's start with the first one is signaling protocols to set up the connection. And this is used to set up, maintain, and tear down the virtual circuit. And it's used in ATM frame relay X.25. And it's an old type of technology. That's why it's not used anymore in today's internet. So in the first step, we initiate call from source to destination. The second step, the destination receives the incoming call, and then the receiver accepts this call, and then in the fourth step, the sender gets the acknowledge and set up the connection. Now we are ready to flow or send the data. So we send the data, and the receiver side, destination part, receive this data. After that, we need to close this specific connection. This circuit is a physical circuit. It's like a wired circuit. So we need to close this specific setup. And let's look at the datagrams, how it works. First of all, this is a connectionless setup, so that's why we don't need any kind of call setup at network layer. So that's why the routers, they don't keep any kind of state information about the end-to-end connection. And then the question, how the packets are forwarded to the destination, it uses the destination IP address. First is just, the network layer received the datagrams from the transport layer by encapsulating the segments into the datagrams, and then blast away, send these packets or datagrams to the network. And then, as I said, each packet, each datagram may take a different path to reach the destination. Can be out of order. And at the receiver side, we receive these datagrams and put them in back to the order. So let's look at the datagram forwarding table. We studied, we know already how the forwarding table works in virtual circuit networks. Now let's look at the forwarding table at the datagram networks. So as you see, it has two main columns: destination address range and the corresponding output link. You know, this in IP version 4, we have about 4 billion IP addresses, 32 bits, you know. Instead of listing all these 4 billion, which is not practical, we provide the IP address range. We say if the header has if the IP address in the header is within this range, then forward these datagrams to this specific output. If it's within the address range too, then direct these datagrams to this output link, and so on. So this is how it works, the forwarding table at the datagram networks. So let's look at some specific example how the forwarding table works in the datagram networks. As you see on the left column, we have the destination address range for the IP addresses. And in the second column, we have the link interface, which are the output of router. So if the IP address falls within this range, then you're gonna forward to this output link. If falls within this range, then you direct this datagram to this output link, and so on. So the next question is, how do we match the IP address in the header to this range in the forwarding table? So one of the common method is called longest prefix matching. So we are gonna, when we look at the IP address and try to match this IP address to the forwarding table, we use this longest address prefix. How these things works, as you see, for instance, we have two examples. Destination address in the IP header is this. So you're gonna match this, the longest one. So as you see, up to here, all these range is same. And then after that, this first range start with 0 and the other range start with 1. So that's why the first one match to the falls within this first range. So that's why we're gonna forward this packet to the 0 interface. And the second example, as you see, after these bits we have the 1, and in this third range we have also 1, but after that it's 0, but this can be 0 or 1. That's why this IP address matched to or falls within this range, the second range, because the longest one matched to this range. That's why we're gonna forward this to the number 1 interface. Okay, so after studying the datagram and the VC virtual circuit network, let's compare both key features, starting with the datagram, which is used in the internet. So in this architecture, the data is exchanged among the computers. So that's why it provides a kind of elastic service, no strict timing requirements. And from the source to destination path, we may have a different type of link. At your apartment, you may have a at Ethernet, and then from your apartment to the ISP center, you may have a fiber optics, and then from there you may have a different types of links. Basically, it's really hard to provide a uniform service. from source to destination, complete fiber optics or complete Ethernet. So at each station, we may have a different type of links, as I mentioned. In this type of networks, we utilize the smart end systems, which are the computers. You can do many things with the computers, right? So you can adapt, you can perform the control, you can recover the errors, bit errors, and so on. So in summary, in this network, in this architecture, the network core is simple and the complexity is on the edge, which is in the computer. So we have a smart, a very complex, complicated end system, which are computers at the network edge. But on the other hand, we have a simple network core in the datagram. Let's look at the virtual circuit architecture, which is utilized in the ATM technology, and it's evolved from the landline telephony that we used in the past at our home, at office, still we are using. So that was developed based on the human conversation. That's why when you talk over this virtual circuit, it provides some guaranteed services, including the strict timing, reliability, and so that's why it has some guaranteed service. But the end system in this case are not smart compared to the datagram networks. They're kind of dummy end system, which this phone at the office, you can dial and talk each other, and you cannot do any kind of processing like computers. So in summary, in this case, the complexity are put on the network core and the simplicity is on the end system. So the end systems, the telephones are simple, but the network core is complex in this case. Okay. Another topics is the router. So we used a router device at this layer. And so let's look at how a router works by looking at the router architecture. So there are two key router functions, as I mentioned. The first one is we run the routing algorithms as well as the protocol, including the RIP, routing information protocol, OSPF, open shortest path first, BGP, border gateway protocol. And the second key function at the router is forwarding. It forwards the datagrams from incoming to the outgoing link. So in terms of hardware or the architecture, and software, we split the router into two parts, which is the control plane is the software and it's responsible for the routing and the management, and the hardware part, which is called data plane, is responsible for the forwarding the packets. So as you see, we have a routing processor that runs this software, which is responsible for the routing algorithms and the management software. And in the hardware part, we have a router input ports and the output ports. And at the middle, we have a high-speed switching fabric. So in this case, the forwarding tables are computed by this processor and pushed to the input ports. So how this packs are pushed to the input, let's look at the details. So this input port consists of 3 blocks. The first one is the line termination, which is implemented at the physical layer in terms of bits. And so they receive the signal in terms of bits or the information. And the second one is the link layer protocol at the second layer, which is the data link layer, such as Ethernet in this case, Ethernet protocol. And the last one is the decentralized switching, which is responsible for the forwarding of the packets. So when you receive a datagram, so we look up a table output port using the forwarding table in input port memory. So the main goal in this block is try to complete the input port processing at the line speed. So this is the line speed. If datagrams arrive faster than the forwarding rate into the switch fabric, then we may experience the queuing. So because the arrival rate is greater than or faster than the switching rate, that's why we need to put this in the queue. That's where the queuing happens. And after the input ports, we switch to the fabric. So how the fabric switch these packets? So it transferred the packet from the input buffer to the appropriate output buffer. So we are talking about two buffers. How this switching is done is based on the buffers. So we have the input buffer, we have the output buffer. We transfer this packet from input buffer to the appropriate output buffer. And the switching rate is an important parameter in this case. What is the switching rate? Is a rate at which packets can be transferred from inputs to outputs. So it's usually often is measured as multiple of input output line rate. So if you have an n inputs, so switching rate n times line rate is desirable in this case. So there are three types of switching fabrics. The first one is memory based. The second one is bus based. The other is a crossbar based. Let's look at each of these type of fabric, switching fabric. Of course, the switching via memories is the one of the first generation switching that is implemented in the first generation routers. And in this case, it's very simple. We have a simple mechanism that the packet is copied to the system's memory. So first of all, you're going to copy this into memory, and then the output port is going to take this packet from this memory. And speed is limited by the memory bandwidth in this case. Let's look at the animation together. So we have a datagrams that we copy to the memory, and then it's passed to the output port. This is how it works in the first type of switching. But there are some problems with the first type, which is the switching via memory. And because it's limited by the memory bandwidth, right? In this case, datagram from input port memory to output memory is done through a shared bus. So in this case, everyone is trying to get this access and take this bus, which we call bus contention. And the switching speed is limited by bus bandwidth in this case as well. Some Cisco router that utilize this method is Cisco 5600, which has a 32 gigabit per second bus. And this is sufficient speed for the access as well as the enterprise routers. But the problem is about the previous switching via bus, shared bus. The performance is limited by the bandwidth of the bus, right? So that's why this third type of switching, which is a crossbar, it overcomes this bus bandwidth limitation in previous method. So Banyan networks, crossbar, other interconnection networks, they're initially developed to connect processor in multiprocessor. So that's why they applied this method to the switching in the routers. So it requires some advanced design, because in this case we need to fragment the datagram into the fixed length cells and switch cells through the fabric. So we split this datagram into the cells, and then we transfer this through the fabrics. So Cisco 12,000 series of switches, they utilize this method, which can switch up to 60 gigabits, 60 gigabit per second using this method. And of course, we comes to a very important slide. Okay, we have the packet. We, pass this push from input ports to the switching fabric, and switching fabric switch to these output ports. Now, what's going to happen? And because in this case, the buffering may require, under what condition? When the datagrams arrive from fabric, switching fabric, faster than the transmission rate. So if the switching rate is faster than the transmission rate, then I need to have a buffer. So buffer is required in this case, so that I can put on the queue. Okay, I put these datagrams on the queue, but the next question, who is gonna go first? So I need to choose among these queued datagrams for transmission. Is it first come, first out, or what kind of scheduling discipline that we are talking about? So because of the queuing, the datagrams can be lost, the packets can be lost because of the lack of the buffers, and then this is gonna lead to the delay, because you need another mechanism to recover this loss. And scheduling is called priority scheduling. Who gets best performance? So you have different customer, you may give them priority in this scheduling, so which is called network neutrality. So of course there are some problems at the output, such as the queuing, as well as we have another call. Okay, I'm gonna explain this queuing in detail, then explain an issue later on. So we said that the buffering is required when the arrival rate exceeds the output line speed, right? And then queuing and loss because of the buffer overflow. So let's look at this. At this time t, this is the time t, I receive the red in the first line. I have the red. In the second line I have the blue, and the third one I have red. So, and these two needs to goes to this output. That's why. So these two red packets datagrams, they need to switch to this red, and the blue one to blue. And then after that, it's time for the green one, and the green one is gonna go to this, and then red is gonna go again this output. So in this case, as you see, if you don't have enough buffer for this red, the buffer overflow happen. So the next question is then, if the buffering is a problem, in order to avoid this, packet loss, how much buffering that I need so that I can avoid or minimize the packet loss? So we have a standard for that, RFC 3439, rule of thumb. Average buffering is equal to typical RTT times link capacity. So simply, buffering is equal to RTT times capacity. For instance, let's say my link has a capacity of 10 gigabit per second and RTT is 250 millisecond. If you multiply 250 millisecond with the 10 gigabits, so the result, the required buffer is 2.5 gigabit you need. But there's a recent recommendation, especially if you have an N flows, data flows, buffering is equal to RTT times over the square root of N. There was an issue about this queuing, related queuing. So the fabric slower than input ports combined, which leads to the queuing may occur at input queues. So the queuing is not only happen at the output, also it can happen at the input port. Under what condition? If the fabric rate is switching rate is slower than input arrival rate. So let's look at this specific problem, which we call head of the line hole blocking. So the queue datagram at front of queue prevents others in queue from moving forward. How this happened? Let's explain. So as I see, we have 3 line and we received 2 red, 1 blue at time t. So they're gonna content race to get the output part, right? So only 1 red datagram can be transferred. So we have 2 of them, but only 1 of them at a time can be transferred. So that's why the lower red packet is blocked. So let's assume that the top upper red is transferred. That's why the lower red packet is blocked. And let's look at one packet after this. And so we transfer this red. Now we have the blue and green packet experiences the whole blocking. Because of this contention, we couldn't transfer this lower red, and the green packet stay at his stage compared to the blue, because blue moved to the next stage and the green is still waiting in his queue. So that's why this red is gonna block the block the green one, which is we call hole blocking. Okay guys, any questions so far? Okay, let's have a 10 minutes break.